So this is day 2 of chemistry prep. Hopefully everybody ended up with the right link eventually. Sorry about that. So today we're going to go over units, unit conversion, scientific measurements, and measurements of properties. And then we're going to start, hopefully, depending on time, getting into atoms, which are sort of one of the most basic building blocks of materials. So starting with units, the reason that we need units is, if you ask me how much water your reaction needs and I say 3, what does that mean? Is that 3 liters? Is that 3 tons? Right? So you need some context about 3 what. So we have an international system of units that are the agreed upon units for some important quantities. And so that's just so that we don't have different scientists in different countries all reporting things in different units, and then everybody has to do all sorts of unit conversions. And so these, just having these agreed upon units gives us a way to all kind of be communicating in the same language. And so we have these agreed upon units for mass, length, time, temperature, the amount of a substance, electric current, and luminous intensity. So in the chat, in the Zoom room, can you guess the SI units for these quantities? So just throw some units in there. Do you think mass is pounds, kilograms, grams? What do you think? Just any of these you think you might know. I'm seeing kilograms, I'm seeing meters, yeah. Any of the other ones too, you can throw in time, temperature. I see seconds, I see pounds, Celsius. I see meters again, temperature in Kelvin. So some people said Kelvin, some people said Celsius. Meters again. Yeah, so it seems like people are pretty confident about mass, length, time, and temperature, and then less so about the other ones, which is totally understandable. I'm seeing joules. Okay, yeah, joules are definitely an important unit. We'll talk about it in a minute. I see volts and pascals. Awesome. So I see amps, I see candela. Either somebody works a lot with light or somebody Googled, which is fine. Okay, so these are the agreed upon units. So mass is kilograms. We'll talk about, some people said grams in the chat, so we'll talk about the conversion between kilograms and grams. Length is meters, time is seconds, which I think people got. Temperature is Kelvin. That said, like that is the sort of agreed upon unit, but people do report things in Celsius pretty often as well. Amount of substance is moles. We'll talk about using moles a little later this week. Electric current is ampere, and indeed, luminous intensity is the candela, which is a fun piece of trivia that I definitely did not know. I have never used this unit, but I also don't work with light that often. So there were some other units that people threw in the chat, especially joules. We'll talk about where those kinds of units come in a bit. But these are kind of, especially the first 5 here are ones that you'll see all the time and should get comfortable sort of with what these units mean. So sometimes we need to convert between different units. And so that can happen if you're given a quantity in non-SI units, or for whatever reason you need that quantity in non-SI units. So to do that, we have conversion factors. For example, 1 mile is 1609 meters, and 1 minute is 60 seconds. That's probably a conversion factor you're used to using a lot in your day-to-day life. We'll talk about how to use conversion factors. For the most part, like I've said a million times and will continue saying over and over again, I really don't like memorizing stuff. Some of these conversion factors, just because you use them all the time, you'll end up memorizing. But in general, these are going to be given to you. And in college, hopefully people aren't going to be testing your memorization of unit conversion. So if you're doing your homework and you need to Google how many meters are in a mile, like in general, that's going to be fine. people are going to be testing sort of your higher concept. I mean, obviously, look at the policies of a given class and ask if you're not sure, but looking up stuff like that is generally, it's going to be in the back of your textbook. It's not a problem. And then the other reason you might need a conversion factor is the order of magnitude might make a number hard to work with. So if you have a number that's like 5 billion and you don't want to keep writing 9 zeros over and over again as you're carrying it around, we use prefixes. So some of you said meters or kilometers or grams or kilograms as our SI unit of length or mass, and those are essentially the same thing. So 1 kilometer is 1,000 meters, and so that kilo prefix means 1,000, and so that's the same as 10 to the third meters. And 1 milligram, that milli prefix, means 1/1000th. And so that's 0.001 grams or 10 to the minus 3 grams. So I'm putting up here a table of some common prefixes. I don't think I ever sat down and intentionally memorized any of these. It's just that as you use the most common ones, you'll sort of accidentally memorize them. So the ones that I think you'll get used to seeing a lot is that kilo and mega are 1,000 and a million. And then in the other direction, centi, milli, and micro are 100th, 1,000th, and a millionth. So we don't use these tens ones that often because like writing 10 instead of 1 is like not that hard. So again, like I wouldn't memorize these, but I would be comfortable using them. If someone says, 10 kilometers and I give you this table, you should be able to say, okay, that's 10,000 meters. Does anyone have any questions on prefixes? Okay, so as always, if you do have questions, raise your hand, unmute, type something in the chat, whatever works for you. So using these conversion factors, for example, 1 mile is 1609.3 meters. Because those things are equal, if we divide them, the answer is 1. So in the same way that 2 divided by 2 is 1, since 1 mile is the same as 1609.3 meters, then if you divide those two quantities, the answer is 1. So that's always the case with conversion factors, in the same way that if I wrote 3 equals 3, then 3 over 3 is 1. So if we want to convert 6 miles to meters, it can sometimes be a little confusing. We know we need to use that 1609.3, but do we multiply by 1609.3 or divide by it? And the way that I think about it, again, never memorize anything, is you're going to need to use that 1 divided by 1. You want to be multiplying by 1, so you're not actually changing anything. And the question is, which goes on top, the mile or the meters? And what you want to do is make sure the units that you want to go away cancel out. So in this case, I'm taking 6 miles, and I want to get rid of miles. And so I need the miles to be on the bottom of that ratio so that the two instances of miles cancel out. And so I have 6 times 1609.3, and that's 9,660 meters. If I had flipped it the other way and taken 6 miles times 1 mile over 1609.3 meters, my final units, nothing would have canceled, and I would have had miles squared over meters, and that is not useful here, right? So I hope that makes sense. I'm going to give you some practice with unit conversions in the next slide. So if you have questions, ask them now, or you can just wait until you're in your breakout rooms and you're practicing. Does anyone have any questions?
So we just by the meters, by the miles we want to convert?
Yeah, so if you, in this case, we want to convert from miles to meters. And so we want our miles to go away. So we have miles in our 6.0 miles, and we want to divide by miles so that those cancel out. So in this case, we multiplied by 1609.3 meters divided by 1 mile. That's our conversion factor. That lump of things is 1. And so we haven't changed the actual quantity of the thing we're measuring, we're just changing the units it's in. And so now our answer is going to be in meters.
Okay. Cool.
So here are some practice questions. Like I mentioned before, you can download the slides. They're on the problem set. This problem is on the problem set, or you can just take a screenshot of this, just because when you go in your breakout rooms, I don't think you're going to be able to see my slides anymore. So in your groups, I want you to do these unit conversions. I'll give you about 5 minutes, so I'll pull you back in around 11 o'clock. Okay, so you should have just gotten invites to breakout rooms. So go ahead and accept those. And I'm going to pause the recording. So those of you who are watching this recording later, you might want to pause it and do this practice for yourself, or you can just keep going, and I'll show you the answers in just a minute when I close the breakout rooms and pull everybody back. Welcome back, everybody. Just gonna wait the 60 seconds for the rooms to finish closing. I hope that was enough time. It's a little hard because I'm not in the breakout rooms and I can't hear you or see your discussions. It's hard for me to know how much time you need. So if you do ever finish the problems like way before how much time I said I would give you, you can always just, send someone back and be like, okay, we're done, we're bored, so that I know and can pull you back. Or if you think you need way more time, you can do that too. Okay, I think most people, if not everyone, are back. So I'm going to go through the solutions. I got a message about whether someone's in the right class. I have actually no idea. So it depends what team you're on. Maybe email Tiffany. I think she would be the one to know. Practicing with units. So converting 2 miles to meters, converting using that conversion factor of 1 mile equals 1609.3 meters. So the answer here is 3,000 meters. Now you might have gotten like 3,200, and I have rounded that down to 3,000, and I'll explain why when we talk about significant figures in a couple slides. And then converting 86,400 seconds into days, that's 1 day. And then 5 times 10 to the 6 meters to kilometers, we're using that prefix. And so we're taking 10 to the 3rd away as that gets incorporated into the kilometers prefix. So that's 5,000 kilometers. And then going the other direction using that those milli, that small prefix, we're going to get 5 milligrams. Does anyone have any questions about how to use those unit conversions?
Yeah, question. Do the one for kilograms and milligrams? Like,
you want me to just talk through it again?
Yeah, if you can, please.
Yeah, no problem. So there's a couple different ways of thinking about this. Great, so I got another question about meters and kilometers, awesome. So 5 times 10 to the 6th meters to kilometers. So I'm gonna do the same thing I did before. I always think about it this way, where if I know the conversion factor, I make that into a ratio, which I know is 1. So 1609 meters divided by 1 mile is 1. And so going back here, I know from this table that kilo means 1,000. So 1 kilometer is 1,000 meters. And so what I can do is take 5 times 10 to the 6 meters, and then I want it in kilometers. So I want kilometers on the top. So 1 kilometer is 1,000 meters, or 10 to the 3 meters. And so I'm going to take 5 times 10 to the 6th times 1 kilometer over 10 to the 3 meters. Those meters will cancel out. And what I'm doing is I'm taking 5 times 10 to the 6th, I'm dividing by 10 to the 3, and that will get me 5 times 10 to the 3. Does that make sense?
Not really. Because you're saying meters and kilometers, but I see kilograms and milligrams, you know?
Oh yeah, so I was talking about the third one, the meters and kilometers.
Oh, okay. Oh, okay.
Yeah, so the fourth one, the idea is exactly the same. So I'm converting 0.0005 kilograms to milligrams. And so I think maybe the easiest way to do that is to convert first to grams, which is sort of our base unit that we're most comfortable with, and then to milligrams. And so 5,000 kilograms to grams, we have, this is why we do prefixes, because all of those zeros are annoying, but 0.00005 kilograms to grams. We want grams at the end. So we're going to put 1,000 grams over 1 kilogram. And then we're going to go to milligrams. And so we know that 0.001 grams is 1 milligram. And so you're going to put 1 milligram on top and then 0.001 grams on the bottom. And then if you multiply through by that, you end up with 5 milligrams. Does that make a little more sense?
So go from kilograms to regular grams and then down to milligrams.
Yeah, that's what I would do.
Okay. Okay, cool.
Yeah, so this table of prefixes, you can think of it just exactly like unit conversions. And so 1,000 grams, looking at kilograms here, or the kilo prefix. 1,000 grams is 1 kilogram. And, 1 billion grams is 1 gigagram, etc. Okay?
Yep.
So, okay. So someone very early on when we were talking about SI units brought up joules. And so joules are a very important unit that we use all the time, but a joule is related to those other SI units. So derived units in general are combinations of SI units. So you might have noticed we didn't have an SI unit for volume, and that's because volume is just length cubed. And so we don't need an SI unit for volume because we have an SI unit for length. And similarly, density is just mass divided by volume. So all sorts of other properties or quantities that we might want to measure are different combinations of other SI quantities. So for example, you might know from physics, F equals ma. That's like the most common physics equation. And so force equals mass times acceleration. And so for me, I never memorize the units of force, because as long as I know that F equals ma, I can figure out what those units of force will be. So in this case, mass times acceleration mass is in units of kilograms, like we've talked about before. That's the SI unit. And then acceleration, don't worry if you haven't taken the physics of this yet, but just trust me for now, that acceleration is in units of meters squared per second. And so force must be the combination of those units. So we have kilograms and we have meters squared per second is acceleration. So force must be in units of kilograms times meters squared per second. And we call that a Newton. So this is the kind of thing that I really, I've never tried to memorize what is a Newton, what is the unit of force, because I can figure it out really easily using these derived units. Does anyone have any questions about derived units or how we relate units to each other? You will get tons of practice with unit conversions all throughout your engineering classes. It's something that is really, really common, both in classes and in practice, that you're given quantities that aren't in the final units you want or need. And you have to convert them, and we have to look up those conversion factors and get comfortable using them. But I guess what I'm trying to show you here is that, it's not just about converting miles to meters and stuff like that. We can also sort of learn something physical from those units. So just as another example, if this is the ideal gas law, which you might have seen in earlier classes, you might not have, it's totally fine if you haven't, but there's this equation that for a gas, pressure times volume equals moles times this constant R times temperature. And so if I want to know what the units of R are, then I can rearrange this equation. And I know that I can just divide over by moles and temperature. So R equals pressure times volume divided by moles times temperature. And then I know the units of PV and NT. So pressure is in units of pascals, for example. Volume is length cubed. And then moles are my unit of moles. And then Kelvin is my units of temperature. So I don't need to memorize what the units of R might be. I can just use this equation that I know to figure out what they must be. Does anyone have any questions about this? So this is called dimensional analysis. And so what that means is we're using the units of the quantities that we're looking at to learn something. I'm going to have you practice with dimensional analysis in just a second. So I use this technique all the time, and it's not directly chemistry, but it's relevant to chemistry and also all sorts of other engineering stuff. So all the time in my work, I come up with an equation that describes, whatever quantity I'm interested in measuring. And I want to check whether that equation makes sense. And so if my equation is right, then the answer better be in the units that I'm looking for it to be in. So what's great about this is you don't need to actually know anything about like what the equation means or where it comes from or anything like that. It's just a really quick check of whether it even is physically possible. So in this case, I'm going to have you practice with the other ones in a minute, but let's say I've come up with this equation that's Q equals M times C times the subtraction of two different temperatures, where Q should be in units of energy or joules. M is a mass, so it's in units of kilograms. This quantity C, which again, you don't need to physically know where it comes from, you just need to know its units. C is called the heat capacity. It's in units of joules per Kelvin times kilogram, and these T's are both temperatures. And so what I can do is, if this equation's right, then when I combine all the units on the right, I should end up with joules so that my Q can be in units of joules. So I'll show you the answer for this first one, and then I'll have you go into breakout rooms and work on the next two. So if I'm looking at the units on the right-hand side, I have kilograms, that's the units of this mass. I have joules per Kelvin times kilogram, that's the units of this C, this heat capacity. And then I have Kelvin, that's the units of this temperature chunk here. And so those kilograms cancel out, there's one on top and there's one on the bottom. The kelvins cancel out because there's one on the top here and there's one on the bottom, and I'm left with only joules. And I wanted my Q, my answer, to be in units of joules. So this equation works. That doesn't mean it's necessarily right, but it's definitely, that would be a quick check where if this didn't work, my equation is definitely wrong. And so this happens a lot. If you're ever on a test and someone gives you a multiple choice that's like, which of these equations is right? And one of them, the units don't even work, you automatically know that that one's wrong. Does this make sense? Does anybody have any questions about dimensional analysis, sort of conceptually? I'll have you practice with these other ones.
Did you kind of just substitute like Q, like joules for Q, and then joules over what is it?
Kelvin.
Kelvin times kilograms.
Yeah, exactly. So I just am looking at what are the units of each of these quantities. So for M, my units are kilograms. So that's where this kilogram came from here. For C, my units are joules divided by Kelvin times kilogram. And so that's this quantity here. And then for this temperature section here, my units are Kelvin. And so I just am looking at the units of the different quantities and then canceling out if there's a kilogram on top and a kilogram on the bottom. I'm canceling those out. And so I'm ending up with this quantity, this right side of my equation is getting units of joules. And so that means that my answer must be in units of joules, which is what I wanted. Does that answer your question?
Yeah, that makes more sense.
Okay. I think there's a hand raised.
Yeah. Is it always going to be joules, right? Because it's for that specific equation.
It's not always going to be joules. It's going to be for whatever equation you want to use. So I'm going to have you practice this next one in your groups. So in this case, I want this E to be in units of energy. So actually in this case, it is joules. But like for this one, you're going to practice your units that you want to end up with is radius. So you want this to be in units of meters, right? And then you're going to do the same thing we did up here, and you're going to take the units of this K, which I've told you is joules per Kelvin, this units of temperature, and then in this case, 6 is unitless. It's just the number 6. Pi is unitless, and you're going to take your units of viscosity, which again, this I'm telling you now that this means viscosity, but you don't need to know that physically to be able to solve these problems. You just need to know the units. So you're going to plug in these units of kilograms divided by meters times seconds. And then your D is in units of meters squared per second. And so you're going to play with those units and see if when you cancel everything out, you get units of meters for the radius. So what you're doing is you're checking, do the units on the left match the units on the right? And if they do, then you're good. And if they don't, you know for a fact your equation has to be wrong. So it's not always going to be joules. It's not always going to be meters. You're just matching the units on the left to the units on the right. I hope that helps a little bit. I'm going to send you into your breakout rooms. If you are like, if your whole room is totally lost, come back and I'll help you out. I'll give you until about 11:25 to work on it together. And again, if you don't finish, that's totally okay. I'll go over the answers when we come back. Okay, welcome back. Just waiting for everybody to come back in after practicing. Does anyone want to share in the chat or out loud how'd this go? Are you totally lost? Does this make sense? Group had trouble doing the third one. Yeah, that third one is definitely the hardest one. We'll go over it in a minute. So I think we're still waiting for about 15 people to come back. Okay, some totally lost. Say that again. Okay, some people are lost, so we'll go through this really slow. No worries, thank you for telling me. Lost is okay, it happens. Okay, I think everybody's back. So conceptually, what we're trying to do is figure out whether our equation is right or not. We don't need to know anything about like the physics of where these equations came from. We're just trying to figure out whether our equation even could possibly be right. And so what's nice about this is no matter how lost you are with like, what even is Q? What do these equations mean? Where is this coming from? All you need is the units. So putting aside the actual process, conceptually what we're trying to do is figure out whether this equation could be right. And so do the units on the left equal the units on the right? That's what we're trying to figure out. So going back to the first example we did, the units on the left are joules. We want to make sure that when we mess with the units on the right, we end up with the units that we have on the left, which is joules. So we take these units of mass, which is in units of kilograms, the units of C, which I've told you are joules per Kelvin times kilogram, and then the units of temperature. So we're just, oh, someone is annotating, hello. So we're just taking the units of kilograms, joules per Kelvin times kilogram, and Kelvin. And we're manipulating those and we're ending up with joules. And so because the units on the right simplify down to joules, then the units on the left are also joules, this equation works, it could be right. Does that like conceptually make sense of what we're trying to do?
Yeah, so like I'll mess around with the right to get the left, right?
Exactly.
Okay.
Okay.
Kind of like the something kind of confusing.
Yeah, so we're just manipulating all of these units to see whether the units on the right equal the units on the left. So now if we go through the units of this second one, again, don't get intimidated by the fact that like, what is Q? Where is this equation coming from? All we need are the units. So in this case, the units on the left, E is energy in units of joules. And we know that joules are 1 Newton of force times 1 meter. Again, like you'll learn that in physics, but I'm just telling you for now that those are the units. And so you don't need to worry about the physics of where all this is coming from. All you need to know is how the units are related to each other. And so I've told you the units of all of the things on the right. So Q is in units of charge, is charge in units of coulombs. This little E, which again, you don't need to worry about what it means physically right now. You just need its units, and I've given them to you. And then R is distance. And there was a question in the chat because R is squared. The units are also going to be squared. And so what we're going to do is we're going to take all those units on the right-hand side. So on the top, we have two different charges, so they're in units of coulombs. So where we have Q times Q, those units are going to be coulombs, C times C. And then 4 and pi are both unitless, so those don't affect our units at all. And then we have this, again, this little e, which again, don't worry about what it means, but its units are coulombs squared divided by joules times meters. And then we have this r squared, where r is distance in units of meters. And so we have meters squared. And so when we cancel all of these things out, we have coulombs times coulombs, and we have coulombs squared. So those are going to cancel. And then we have joules kind of doubly on the bottom. So we're going to end up with joules on top. And then when we look at these meters, we're going to end up with 1 meters left over. So our final right-hand side units are in units of joules per meter. But we wanted our units only in units of joules. And so the left-hand side and the right-hand side don't have the same units. And so this equation doesn't work. Does that make sense?
We go up.
Yes, that makes sense.
Okay.
Wait, so it's not understanding like why you put the J up, you know?
Yeah, so
Is it like inverse or something?
I think, yeah, so how does the J end up on top, I think is the question here. And so this is just playing with fractions. So I have this big fraction, which has stuff on top and stuff on the bottom. And then the joules is on the bottom again. And so it kind of, it's like doubly on the bottom. And so it cancels out and it ends up on the top. So if I had 1 divided by, let's see if I can draw. If I had 1 divided by 1 over 4, sorry, that's a 4, then the answer would be 4. So that's how the joules ended up on the top again. And then, yeah, there's also a question about what happened to the 4 and the pi, and the people who are answering it are totally right. The 4 and the pi don't have units. And so they totally matter in this equation, but when I'm just analyzing the units, they don't have any units, and so they're not going to affect this type of dimensional analysis. So I'm just trying to give you guys this as a tool so that if you're in your engineering classes and you come up with an equation, this gives you a way to check whether your equation makes sense at all. I see a hand raised. Yeah.
Squared and meter squared, you know?
Where did the meter squared come from?
No, where did the square go? Because when you do the equal, it's just joules divided by meters.
Yeah, so I had meters squared right here, but then I have a meter, 1 meter here. And so 1 over meters times meters squared just gives me meters. And so it's like saying if I had 2 squared over 2, the answer is 2. So in this case, I had meters squared divided by meters, and that ended up with meters over here. And so my answer on the right-hand side is in joules over meters, but the thing I wanted on the left-hand side, that E, I wanted in units of joules, and so those are not in the same units. So that's kind of an example of how to use this. The third question I gave you, I think is really hard because there are a lot of units going on here. So I'm just going to go through it quickly, and then I'm going to show you a tool or a trick that makes it a little easier. So this one was wrong because the left-hand side and the right-hand side are not in the same units. So the first thing I'm going to do is the same thing I did before. I'm just going to plug in the units of each term in my equation. So this K on top, I told you, is in units of joules per Kelvin. So I'm just going to put joules per Kelvin right here. The temperature, this T is in units of Kelvin. So I'm going to put a Kelvin right here. And then on the bottom, just like before, I have a 6 and a pi. Those are unitless. So I'm not going to put their units in this analysis at all because they don't have any. And then this little n, it's called eta, which again, you don't need to worry about the physical meaning behind it, is going to be in units of kilograms divided by meters times seconds. So that will be the units here. And then this D is in units of meters squared per second. So at first, it kind of looks like, okay, maybe I can do some stuff with these meters. I can do some stuff with these kelvins, but there's still going to be like joules and kilograms, and there's no way I'm going to get back down to meters. But joules are a derived unit. And so a joule is actually a Newton times a meter. And so we can expand out these joules. And so you can see how this can get really complicated. So the T stays, the T is in units of Kelvin. So that's where this Kelvin came from. And then what I've done is I've expanded the units of joules. And so this totally works, but it gets really complicated really fast. And it actually turns out that this is correct. When you cancel all of these out, the kilograms cancel, the seconds all cancel, the kelvins cancel, and you end up with just 1 units of meters. But there are a lot of things going on here. And so there's a trick that makes this a little bit easier that I can show you now. But I mean, does everybody conceptually understand what we're trying to do? Okay, I am getting a yes in the chat. Oh, I love seeing all of these yeses. If the answer is no, that is also okay. But I'm gonna move on, and if you are still confused, just stay after class. So there's this tool called Wolfram Alpha, which I didn't know about in high school. Maybe you guys are a more tech savvy generation than mine. But there's this tool called Wolfram Alpha. And so I'm just duplicating the question that I asked on the previous slide. Radius equals this equation. And what you can do in Wolfram Alpha is it is really good at a whole bunch of stuff, but one of the things it's really good at is unit conversions. So what I can do is just type out this equation, and I'm typing out the right-hand side, and I'm just making up numbers, but I'm putting them in the right units. And so for K, I'm putting in 1 joule per Kelvin. For the temperature, I'm just putting in some temperature in units of Kelvin. And then on the bottom, I'm putting 6 times pi. I'm putting 1 kilogram divided by meters times seconds. So I'm putting in something in these units of viscosity, these units I've given you here. And then I'm putting in some number in units of meters squared per second. So in this case, I'm just making up the numbers, but I'm getting the units right. And then I hit enter, and it will do all of the unit conversions for me, and it will give me an answer in units of meters. And so because I made up those numbers, like the actual 15.92 is meaningless, but this is just kind of a shortcut to get Wolfram Alpha to do all of this unit conversion stuff, converting, joules and kilograms, and telling us what the final units are in. So I use Wolfram Alpha literally every day. And I definitely used it on my homework and my engineering classes. So you want to get comfortable doing this without the internet, just for tests and stuff. But this is a really useful tool that can be really helpful on your homework. Does anyone have any questions about what I'm doing here or why Wolfram Alpha is useful? I will happily evangelize about how amazing Wolfram Alpha is whenever I'm asked. So just to reiterate, all I'm doing is putting in random numbers that are in the correct units and seeing if it gives me an answer that are in the units that I want it to be. So I'm doing exactly the same thing that I did on the previous slide. It's just that Wolfram Alpha needs a number in front of the units. Does anyone have any questions on units?
Can you walk through C again?
Yeah. If I can make it go back. Okay. So the first step always is to just plug in the units that we want to use. And so this K here is in units of joules per Kelvin. So I put that here. The T is in units of Kelvin. So I put that here. The 6 and pi don't have any units. So they don't factor in at all here. And then this is called eta, the little n thing, is in units of kilograms divided by meters times second, which I gave you here. So that's what I've put here. And then the last thing, D, is in units of meters squared per second. So I put that here. So I haven't had to worry about where this equation comes from. This happens to be an equation that I use a lot of times in my research, but the beauty of this trick is that you don't need to know where it came from. So that's step one, is you just plug in all of the units. And then the next thing I'm going to do is expand everything into SI units. And so this is kilograms, meters, second, Kelvin. So these three terms are already in fully SI units. But this one, the joules, are not an SI unit. Joules are a derived unit related to force and distance. And so if you look up what a joule is, or you can figure it out from sort of, it's a unit of force times a meter. And then force is a Newton, which you can get from F equals ma, but you can also just Google it. A joule is a kilogram times meters squared divided by seconds squared. And so these three units came from me expanding what a joule is. And then I kept that Kelvin on the bottom, so the Kelvin stays here. And so then what I'm going to do is this thing on the right is the same as the thing on the left. And then I'm going to start just canceling out units. And so this Kelvin and this Kelvin, one's on the top and one's on the bottom. So those cancel. This kilogram and this kilogram cancel. There's 2 seconds on the top up here, and there's 2 down here. So those cancel. And then this meters squared can cancel with this meters squared. And so all I have left, just like up here, is I have this 1 meter. And because it's kind of doubly on the bottom, it ends up on the top. And so all that's left is this meter unit. And I wanted my left-hand side is a radius in units of meters. And so that works. The right-hand side and the left-hand side are in the same units as each other. But like we kind of talked about, that is a lot of work to go through and expand all of those units back and forth. And so I can solve that exact same problem by just asking Wolfram Alpha to do those unit conversions for me. Does that help a little bit?
Yeah, so you can just look up what joules is to expand it, and it'll be fine.
Yeah.
Thank you.
Yep. Okay, so the last thing I want to talk about today is significant figures. So some of you might have seen this in your previous classes, but people with PhDs still get this wrong all the time. And so I just kind of want to emphasize why this is important. So any measurement you're ever going to take has some amount of uncertainty. You're never 110% sure of anything you're measuring. And it's important for us to convey that. So when you look at a number, you can determine how many significant digits that number has. So any number that's not 0 is significant. And then zeros between non-zero digits are also significant. So for example, the number 101 has 3 significant digits. But leading zeros are not significant. So if I have 0.234, all that 0 is doing is giving me sort of how many tens places are there. And so that number has 3 significant digits. And then if there are trailing zeros to the right of the decimal, those are significant. So 0.400 has 3 significant digits. So what that means is I am sure that this number is 0.400. It's not 0.410. It's not even 0.401. It's like exactly 0.400. But, and if there is a decimal point after the zeros, those are also significant. So 2000 has 1 significant digit. So what I mean if I write 2000 is it could be 2001, it could even be 2010. All I know is it's like around 2000. But if I write 2000 with a decimal point there, that means it's exactly 2000. It's not 2001. And then if I write 2000.0, because that 0 is to the right of the decimal point, that is 5 significant digits. So that 0 is also significant. Does anyone have any questions about just using these rules? Yeah.
So basically the only way it's not a significant figure, like if the 0's in the front?
If the 0's in the front, it's definitely not significant. And then if the 0 is towards the end and there's either no decimal point, like in 2000, that's it, yeah. So if the 0 is in front, it's not significant. And then if the 0 is at the end and there's no decimal point, then it's not significant.
Okay.
So for
So
example,
Mhm.
I was gonna say, for example, the last one, the 2000, if it would have been like 2001, then it would have been 4 significant digits.
Exactly. 2001 would have been 4 significant digits. Because I wouldn't put that 1 there if I wasn't sure. I would have just called it 2000, right? I've never been like in a crowd of people and been like, huh, there's about 1,005 people here, right? But I might say there's about 1,000 people here.
So in 0.01, there's only 1 significant digit.
Correct. Good job.
Okay, thank you.
Yep. So how do we use these? So the first application is in addition and subtraction. So this is a fancy way of saying you just need to look at like I'll just show you an example. So you find the significant digit that's in the smallest decimal place for each value. So in this case, I have 2.45 plus 0.375. This one, the 2.45, has a significant digit in the 100th place. And this number, 0.375, has a significant digit in the 1,000th place. Sorry, that's hard to say. And then we just add or subtract the numbers. You just plug it into your calculator. So in this case, my calculator would tell me the answer is 2.825. But then I have to round it so that the final answer has the one that's sort of the least precise. So in this case, 2.45 only goes to the 100th place, and this goes to the 1,000th place. I should have picked numbers that were easier to say. And so I have to round my answer to the 100th place. So my answer is going to get rounded to 2.83. So the way that I remember this is, let's go back to my example. Let's say I'm at a concert and I say, wow, there's about 2,000 people here. If one more person walks in, I'm not going to be like, there are precisely 2,001 people here, because I wasn't ever sure that there were exactly precisely 2,000. So if I have a crowd that's like about 2,000 people and 5 more people walk in, it's still about 2,000 people. So I need to round down to however sure I was before. Does this make sense?
Not really.
Okay,
I don't know,
so
it's kinda hard to understand.
that's okay. Totally okay. Thank you for speaking up. So basically what I'm trying to do is figure out how sure I am for each of my numbers. So going back to my example with a crowd of people, if I say there's about 2,000 people at this concert, I'm pretty confident there's not 10,000, right? But it could easily be 2,010 people. I just know there's like roughly 2,000 people. And so then if 2 more people walk in, even if I'm totally sure that exactly 2 people walked in, I can't now suddenly say there are exactly 2,002 people here, because I wasn't ever sure that there were exactly 2,000 people here in the first place. So
I think
what?
I don't understand the addition portion. 'Cause, like, usually you align like the decimals and then just fill in the rest, right?
Yeah, so the addition part is not changing at all. So all I've done here is take 2.45 plus 0.375. You're going to do the actual math exactly how you're used to. So 2.45 plus 0.375 is 2.825. That has not changed. So yeah, maybe I should have written it a little differently, but 2.45 plus 0.375 is 2.825. That's just addition. And so the only thing that I'm trying to change is how we then round our answer. Does that make sense? So the actual part of like doing the math of doing 2.45 plus 0.375, that has not changed. That's 2.825. But then what we're trying to do is figure out how to round our answer. And so because I was only sure about 2.45 to the 100th place, then I can only be sure about my answer to the 100th place.
Okay, I think it's just the placement that was kind of making me, kind of get confused, but I understand now. Yeah.
Okay, cool. Yeah, I totally get it. I should have sort of shifted it over a little bit as I just wrote it on the screen. So the last thing I want to do today is talk about multiplication and division. So for multiplication and division, all we have to do is count the significant figures. So I'm going to count the significant figures in each number. So in this case, I have 10.2 times 0.40. So practicing our rules, this 10.2 has 3 significant figures, and the 0.40 only has 2, because this 0 in the front is not significant. And so we're going to just multiply or divide the numbers exactly how you learned in high school or whatever, plug it into your calculator, you're going to get 4.08. But then we have to round our final answer such that it only has as many significant figures as the least confident one we were before. So we had 3 sig figs and 2 sig figs. So we have to round our final answer to 2 significant figures. So we're going to round our answer to 4.1, which has 2 significant figures. And so going back to like my example of the concert, if I say there's about 2,000 people here, even if I know that exactly half the people leave, I don't know that there's exactly 1,000 people left because I wasn't ever sure that there were 2,000 people to begin with. So all I can say that there are about 1,000 people left, But because I wasn't ever sure that there were 2,000, I can't be sure of exactly how many people are left, even if I'm sure that exactly half the people left. Does this make sense? Okay. So there are a bunch of practice problems. I'm going to stop here for the day. There are a bunch of practice problems on the problem set. There's also some extra problems because I wasn't sure how far we get today. So right after class, I'm going to edit that to remove sort of the practice problems that we didn't get to today, which is totally fine. Yeah, that problem set is probably going to change in about half an hour. So if you want, you can start on the first half, but there's going to be problems that we didn't get to that I'll remove from the problem set in a minute. But yeah, I'm going to stop there. And obviously, if anybody has any questions, please feel free to stay after. I'll be here.